Hello, everyone. I hope you are all well. Welcome to today's session where we're looking at the second part of Learning Unit 5, which is conducting a hypothesis test for single mean, but now where we do not know the value of the population standard deviation. So as you will see here, we're looking at when the population standard deviation is unknown. And as I had mentioned to you, same idea that we follow as we had in Learning Unit 4, which is where when the population standard deviation is unknown, they will give you the sample standard deviation in place of it. So the sample standard deviation will be given. And instead of using a Z value as your critical limit here, we now use a T value as our critical limit. So we need to refer to table 2 of your appendix. And remember, in order to get to a T value, you need two things: an A value, which is a level of significance, which they will provide you with. And then you also need a degree of freedom. And in this case, you're going to have it calculated as n minus 1 as well. So pretty much the same idea as with Learning Unit 4 when it comes to a population standard deviation being unknown. And you'll see that the same exact steps are followed where we first determine the null and alternate hypotheses. We then look at what your region of acceptance and rejection is. We then calculate the test statistic and compare it to the regions of acceptance and rejection and look at where does it fall. And then we decide and determine whether we are accepting or rejecting and conclude. We need to give some sort of idea or closing statement which pertains to what we actually mean when we say that we accept the null hypothesis or we do not reject the null hypothesis, or alternatively, if we're saying that we do reject the null hypothesis. So the example here is one of an upper-tailed test, and it says a company that manufactures cans of cold drink regularly take samples of the cans to test if the volume is at most 330 ml. So by saying at most 330 ml, they're saying that 330 is the limit and it's everything below that or inclusive of it as well. So what they're essentially saying here is that it's everything less than or equal to 330. And as you can see here, we have included the equality sign below the less than sign, which indicates to you that this statement can actually go into our null hypothesis, because remember, our null hypothesis requires the equality sign to be included in it. It's one of the defining characteristics of hypothesis testing that our null must always have the equality sign included. So already we find that the statement that had been made in that first sentence, that they would like to test if the volume is at most 330 ml, this is definitely going to be included in our null hypothesis. And then they say to you the most recent sample of 120 cans, so n is equal to 120, and it found that there was an average of 328 ml, which is then our sample mean, so 328, and there was a standard deviation of 10 ml. So they haven't specified here that it is a population standard deviation. And if they don't specifically include in words that it is a population standard deviation, we make the assumption that it would be a sample standard deviation. But we could also gather that from the fact that they said of the sample of 120 cans, this was found to be the standard deviation. So your sample standard deviation, which is denoted by the symbol S, is then 10 ml. And they asked you to test the hypothesis that the cans of cold drink have at most 330 ml at a 1% level of significance. And again, remember here, we said that when they're saying at most 330 ml, they mean that 330 ml is the maximum and it's referring to everything inclusive of that or below it. So the first step, which is to write out our null and alternate hypotheses, is to firstly, since we're working with the mean, as you could see from the information provided, they were looking at the average volume in a. So we're using the symbol mu, and then what had been questioned here of at most 330 ml, which is saying less than or equal to 330, would go into our null hypothesis. And our alternate would say that it's looking at everything greater than 330 ml. So from this, as I had said to you in the previous video, if you are confused about what type of test it is, just look at the sign in your alternate hypothesis. If it has the not equal to sign, which is the one that looks like this would mean that it is a two-tailed test. If it has a greater than sign, it's an upper tailed test, like in this case. And if it has the less than sign, it is a lower tailed test. So in this case, since we have the greater than sign in our alternate hypothesis, it said to us that it is an upper tailed test. So once we know that, it tells us what we need for step 2, which is firstly to draw up the bell-shaped curve, which would assist us in determining our region of acceptance and rejection. Since it's an upper tail test, remember there's only one critical limit. So the critical limit is on the right-hand side for an upper tail test. That means everything further to the left or inclusive of the critical limit itself is your region of acceptance. Everything above this value is your region of rejection. So now we want to know, how do we know the value of the critical limit? This is where the t-value comes into this section. We then need to determine the t-value by looking at what our level of significance is. Like I said at the top, your level of significance, they said to you, was 1%. So A is equal to, you convert that to a decimal, so 0.01. And then you need your degree of freedom, which is calculated as n minus 1. And in this case, n is equal to 120 minus 1, which is 119. So we're going to take 0.01 and 119 to table 2 of your appendix, which I'm going to put now. Okay, so as you can see from this, remember we're looking for A being equal to 0.01 and a degree of freedom which is 119. So for 0.0, locate it going across the table in the first row at the top. 0.01 is the fourth column. And then we're looking for your degrees of freedom going down the table. And if you look at this at the bottom, which is increasing, so we're looking at your higher numbers towards the bottom of the table, you're looking for the number 119. But as you can see, they go from 90 to 100, and then 110, and then 120. Now, in a case like this where you cannot locate the figure itself, you're going to look at what figure it lies closest to. So here they have 110, and then it goes to 120. So you're going to look at, does 119 fall closer to 110, or does it fall nearer to 120? In this case, it would be closer to 120 since it's just one off. So you're going to look at in line with 120 and in line with the 0.01 at the top, your critical limit is 2.358. So this is then the limit you will use in your diagram. So when we draw up that bell-shaped curve, this is going to be 2.358. So let's go back to the question and we can continue with that. So as we had said here, remember your your null and alternate hypotheses. Your null said that it was less than or equal to 330 mLs. Your alternate said that it would be greater than 330. We drew up your bell-shaped curve. We know that this is your region of acceptance. This is your region of rejection. And we had said that using the values of A being 0.01, and the degree of freedom of 119, we got that your t value was 2.358. So in this diagram, 2.358 is your critical limit. Remember, anything inclusive of the 2.358, so including that limit or lower than it, is your region of acceptance. Anything greater than it is your region of rejection. So you would write out in words that you would accept your null hypothesis if your Z statistic, which you'll be calculating in the next step, is less than or equal to 2.358, and you will write out your rejection region, being that you will reject the null if your Z statistic is greater than 2.358. So something that I had forgotten to mention to you in the previous recording is that when you write out these regions of acceptance and rejection, you generally are only required to write out the rejection region. You don't have to write out the acceptance region. But again, for your own benefit, if you do find that it is useful to write out both of these, and again, in terms of the diagram as well, if you find that it's useful to have it drawn up, then it's perfectly fine to do so. But the mark allocation is only for writing out your region of rejection. Okay, so we know your region of acceptance and rejection. Now to calculate your Z statistic, which remember for a mean is calculated as x bar minus mu over the standard deviation over the root of n. Your x bar we said was the 328 minus your mu, which is the population figure, was just the 330. This is over your standard deviation, which was 10 over the root of n, which was 120. So this would give you a Z value of minus 0.89. And then in step 4, you're then going to take this value and look at where does it fall on your bell-shaped curve. So it would fall somewhere to the left. Remember, it works as a normal number line, so your negative figures would fall on the left. And this would be in your region of acceptance. So you would then therefore say that therefore you will accept the null hypothesis, or you can say that therefore we do not reject the null hypothesis, which is the same as saying that we accept it. So you can say therefore we do not reject the null hypothesis, and this indicates, so indicating, and if we're saying that we accept the null, we're saying that this is true, which means that what they were saying about the volume being at most 330 ml was actually true. So this indicates that there is at most 330 mLs per can. So there is at most 330 ml per can. Okay, so that is your test for a single mean when the population deviation is unknown. We've been given the sample standard deviation, and so as a result, we use a t-value. Your t-value, you require the level of significance and the degree of freedom for it. We go to table 2 of your appendix, locate what the t-value is, and we use that as our critical limit. The rest of it is pretty much exactly the same, how we go about the steps, and again, how we calculate the Z value as well. that is it for today's session. I will next be looking at the hypothesis test for a single proportion. And you'll see there as well, the steps are pretty much exactly the same. It's just that we'll be working with a proportion. So the Z value formula is slightly different, but everything else is exactly the same. Thank you guys. Cheers.